Okay, let's have a look at this concept called the reaction quotient and how we can use this reaction quotient to determine whether a reaction is at equilibrium or whether it's going to shift towards the reactant side or the product side. Now there are three steps in determining this question. The first one is that we need to calculate what's called a reaction quotient, sometimes written as a trial equilibrium constant. And we do this the same way that we calculate our equilibrium constant. We get the concentration of our products over the concentration of our reactants. But instead of using the concentration at equilibrium, we use our initial concentrations to calculate this value. The next step is to compare this reaction quotient with our equilibrium constant. And one of three things will occur. Either our reaction quotient will be larger than our equilibrium constant, in which case our reaction will shift to the left, or our reactant side. To get a larger value of Q, it means we must have a larger concentration of products. So the system will shift to reduce that concentration, and the only way that it can do it is to shift to the left-hand side. If Q is equal to our reaction constant, our equilibrium constant, the reaction is at equilibrium. And then lastly, if our reaction quotient is smaller than our equilibrium constant, the reaction will shift to the right, because relative to our equilibrium constant, the concentration of reactant is too large, which will mean that it will need to be reduced as it moves toward equilibrium, so the reaction will shift to the right. Let's have a look at this in action. We've been given a question to determine how the following reaction will proceed, whether it will shift to the left, shift to the right, or whether it will be at equilibrium. So our reaction, we've got 2 moles of SO2 reacting with 1 mole of O2 to give us 2 moles of SO3. We've also been given the equilibrium constant as 0.15. And you'll notice we've been given 3 sets of concentrations, all our initial concentration, and we're asked to determine whether this will shift to the left, shift to the right, or be at equilibrium. So the first step is to calculate our reaction quotient. And as I said before, we do it exactly the same way. We get the concentration of our products over the concentration of our reactants, and we substitute our values in for our concentrations. So 0.056 to the power of 2 for our SO3, 0.34 to the power of 2 for our SO2, times 0.172 for our reactants, and this gives us a value of 0.154. Now our last step is to compare this value for our Q with our KEQ. In this case, 0.154 is greater than 0.15, and because it's greater, our reaction will shift to the left to move toward equilibrium.